Hello everyone, my name is Mritunjaya Parashar and I am a PhD student in University of North Texas, USA. My research advisor here is Professor Anupama Kaul and I am working under her supervision in Nanoscale Materials and Device Laboratory here at UNT. My topic for today's presentation is contact engineering of inkjet-printed organometallic halide perovskites for photodetectors and solar cells. Now, before we move on with the presentation, let me introduce all of you with my group's research. Our group focused research on nanomaterials such as graphene and nanocarbon, two-dimensional transition metal dichalcogenides, black phosphorus, perovskite, quantum dots, etc. For their synthesis, we rely on techniques such as chemical vapor and physical vapor depositions. We also have capability of using few additive manufacturing techniques such as inkjet and 3D printing. For the air-sensitive materials processing, we use glove box, and we also use one of the UNT shared facility, which includes a clean room. To study the electrical behavior of these materials, we have an IV station from Lakeshore Cryotonics, which has cryogenic capabilities to go down to temperature as low as 4 Kelvin. We also have different lasers which can go from 300 nanometer to 1100 nanometers. We have a instrument from Horiba system which include temperature dependent photoluminescence and Raman spectroscopy, atomic force microscopy, and tip enhanced Raman spectroscopy, and few of the others characterization that we use from UNT shared material research facilities, which is SAM, XRD, XPS, etc. Now, for the application of these materials, we are mainly interested into flexible electronics, which includes photodetectors and solar cells and sensors, gas sensors, etc. Now, these are few of our group's research works that were published in some of the reputed journals. You can see them here. Now, before moving on, let me first talk about the perovskite structure. So, perovskite is a crystal structure which has a type AbX3, where A, B, and X are nothing but different cations and anions, and they occupy different certain sites in the crystal. Now, A is usually organic or inorganic cation, such as methylammonium, formamidinium, butylammonium, or cesium, etc. B is usually a divalent metal cation, such as tin or lead, and X is usually a halogen anion, which is chloride, bromide, iodide. Now, these perovskite materials have remarkable properties such as long charge carrier lifetime, wide absorption range, long diffusion lengths, and low recombination rates, etc. That is one of the reasons these materials are one of the great candidates to be used as photoabsorber layer in photodetectors and solar cells. Now, in our work, we focused on two-dimensional perovskite materials because 2D materials have few exceptional properties such as spatial quantum effect and tunable optical band gap. Now, these perovskite materials, their band gap can be changed by either changing the halide concentration. As you can see here in this figure, the PL peaks are shifting with changing the halide concentration or changing the halide completely. Or we can change the number of two-dimensional materials layer. Here you can see the different layer of 2D perovskite material has different PL peak positions. Usually perovskite photodetectors, not just perovskite photodetector, in fact, photodetectors are of two types generally. One is top-down, which is called vertical structure, and one is lateral structure, which looks like this. This also looks like a field effect transistor. Now the study that I'm going to present is published in Nature and Feature 2D Materials and Application from our group. In this work, we have done fully inkjet printing of perovskite ink on a polyimide flexible substrate, and also the top electrical contacts, metal contacts, were also inkjet printed, which are graphene and silver. Now this is showing the optical and electrical characterization of 2D perovskite photodetectors. Here you can see that the temperature dependent IV characteristics of graphene and silver perovskite photodetectors, and the you can see the IV characteristics is showing a shift in their shape with the different temperatures. Here you can see the barrier height voltage variation with voltage for both graphene and silver perovskite, and we have used this to calculate the Schottky barrier height at 0 volt, which is around 0.92 electron volt and 0.712 electron volt for graphene and silver perovskite photodetectors in temperature region of 100 to 150 Kelvin. Now these two are showing the photocurrent response with time for graphene and perovskite and silver and perovskite photodetectors. And these two figures are showing the rise time and fall time of graphene and silver perovskite photodetectors with temperature. Here we have studied the wavelength dependent photocurrent for both these perovskite in different temperature region. At around 630 nanometer, the photocurrent was found to be maximum, which is consistent with the band gap of the 2D perovskite that we have used. The external quantum efficiency of both of these perovskite photodetectors can be found to be exceeding the 100% at around 350 Kelvin. The on-off ratio of these perovskite photodetectors can be seen varying with different temperature in this figure. Now, since these photodetectors were fabricated on flexible polyimide substrates, so we expose them to bending and we check the photocurrent with different bending curvature and with different fluence of incident light, and that variation can be seen in this figure. So the next part of our work is perovskite solar cells. Although we want to develop fully inkjet printed 2D perovskite solar cells, but working with 2D materials can be a little bit tricky. So first we are trying to optimize the cell structure in our lab using a commonly used three-dimensional methylammonium lead iodide perovskite. So to characterize the photoabsorber MAPBI3 layer, we use SAM and XRD. So here in this figure you can see the grain size of the MAPBI3 perovskite is quite good, but the number of pinholes can be evident in the figure, like here, here, and here. And also from the XRD, we can see at around 12.6 or 7 degree, there is a small impurity peak of PBI2. Although the crystalline peaks of perovskites are evident from XRD, but still there is a small impurity peak. Now this is our perovskite solar cells measurement setup. This is the source meter that we are using, and that's how our cells look like. The active area of our cell is around 0.0256 centimeters square. The structure of the cell that we are making is NIP type, which include FTO, compact TiO2 perovskite layer, and a Spiro-MeOTAD layer, and top contact, which is silver in our case. So TiO2 and Spiro layers are used as electron transport and hole transport layers respectively. So far the cell which achieved highest efficiency in our lab as PCE at around at 8.73%. These results are not as good as the reported result for the same type of cell structure, but we are continuously trying to improve these results, and we are sure that we will improve them in future activities. So to summarize, we have fabricated fully inkjet-printed two-dimensional perovskite photodetectors using graphene and silver inks on flexible polyimide substrates. The on-off ratio and response time for these perovskite photodetectors were found to be quite higher than the prior reports. Also, our second part of the work, which is related with the development of two-dimensional inkjet printed perovskite solar cells, that is in progress. We are currently optimizing the 3D perovskite solar cell structure, and we are continuously working towards that goal. These are the relevant references that have been used in this presentation today. And we would like to thank our sponsors, Office of Naval Research, National Science Foundation, and our university. Thank you.